So I'm sure most of you know, but just as a reminder, thermal infrared remote sensing is a really powerful tool. If the Diviner team hasn't beaten you over the head yet about this idea, hopefully by the end of this talk, I will. So from thermal infrared remote sensing, we have the ability to map temperatures, composition, and thermophysical properties across any planetary body. And for the moon, we're really lucky because we've had Diviner in orbit since 2009, making measurements of the surface at all times a day. And so from Diviner, we've gotten temperature maps showing the full range of surface temperatures of the moon, including the coldest spots and the permanently shadowed regions. And then we've also been able to use Diviner to see the compositional and thermophysical diversity across the lunar surface. Excuse me. Soon, we will have in situ measurements of the thermal infrared signature of the moon using the Lunar Compact Infrared Imaging System, which we also call L-CIRiS. L-CIRiS is a rebuild of Ball's CIRIS CubeSat, which is currently in low Earth orbit collecting data. And the L-CIRiS design includes an onboard calibration system, as well as 3 narrow channels that allow us to do compositional studies, and then 1 broadband channel that allows us to do thermophysical studies. And I should note here that of these 3 spectral channels, 2 of these channels, bands 2 and 3, are similar to the Diviner band passes, and all 3 of the spectral channels overlap with the Trailblazer thermal instrument. And so we'll get nice correlation between all those data sets. So as far as our spatial resolution is concerned, at about 3.6 meters from the lander, we will be getting spatial resolutions on the order of 0.7 centimeters. And at about 100 meters from the lander, we'll get spatial resolutions on the order of 40 centimeters. And we have 3 main objectives with the mission. The first is to map the thermal infrared composition across the landing site. And we'll be doing this at the centimeter scale. And so what this is really going to help us with is we're going to be able to use these small scale compositional maps to ground truth observations from the Diviner instrument, as well as Lunar Trailblazer. And it'll give us an idea of the sub-pixel mixing of mineralogies that we're seeing in these orbital data sets, as well as give us an assessment of how surface roughness and thermal gradients at the very small scale play into our compositional maps. And for those of you that are interested in the compositional aspect of our investigation, I do have a poster that I'll be presenting tomorrow evening. Our second objective is to estimate the thermophysical properties of both the regolith and the rock that are around the landing site. And so by making measurements across the lunar day, we can estimate the thermal inertia across the scene at, again, the centimeter scale. And this will give us a better understanding of what thermal inertia is of actual lunar rocks on the surface. These thermophysical studies will also allow us to characterize the geotechnical properties of the regolith around the landing site, which will help us provide feedback for future exploration with both rovers and tools, and also with humans. And then our final mission objective is to characterize the small scale thermal gradients and micro cold traps at the south pole of the moon. And what we can see here in this top image is that as you go to smaller scales, the surface roughness and the shadowing increases. And this increase in surface roughness and shadowing creates really steep thermal gradients at the smallest scales. And it's this thermal signature that dominates or provides a huge contamination factor into our larger scale Diviner and moon mineralogy mapper observations. And so these are effects that we typically need to correct for. And so the L-CIRiS in situ measurements that we will be obtaining will be able to test whether or not these micro cold traps exist, measure the thermal gradients across these small scales, and will provide a ground truth for removing these effects from our larger data sets like Diviner and Moon Mineralogy Mapper. L-CIRiS is currently planned for launch and surface operations in late 2023. It's part of the CLPS 19C mission to Hayworth Crater at the South Pole. Other instruments that are on that lander include Heimdall, which includes a suite of imaging systems, including a descent imager and a wide angle and regolith imager. There will also be the Moon Ranger rover that will carry a neutron spectrometer, which will provide complementary data to our temperature maps. And then there's also a sampling mechanism called Sampler. As you can see here, Ball Aerospace has completed the build of L-CIRiS. So here is a picture of the flight model. It is currently undergoing integration and testing, including this week is doing TVAC testing, and we are on track for delivering the instrument to NASA next month. Now, when we're at the surface, this image here gives you a concept of where L-CIRiS will be mounted on the lander and what kind of observations we'll be able to do during the mission. And so you can see that L-CIRiS here is mounted approximately 1 meter off of the lunar surface. And so again, the closest we'll be able to see to the lander is at about 3.6 meters. Again, the resolution at that distance will be about 0.7 centimeters. From there, we'll also be able to see all the way out to the horizon. And so that will give us the capability to take panoramic images across the landing site scene. We do have the ability to rotate and get azimuthal scans. And so we'll be able to get a 180-degree azimuthal scan around the landing site. And we're able to do this once every 4 hours. And so we will be able to get many observations throughout the lunar day to really constrain the thermophysical properties. So just to summarize, the L-CIRiS, the L-CIRiS science and put these into perspective. The thermal infrared can be used to really map these micro cold traps. And so we're going to be able to use L-CIRiS observations to test whether or not these cold traps exist. And if they do, be able to measure the temperature within these cold traps. We will be getting the first thermal infrared measurements of the surface, including compositional maps. And it's these compositional maps that will provide a really important ground truth and a link between sample science and our remote sensing science. And ideally, and luckily, we will be going to Hayworth Crater. We would like to be in an area where we can measure lots of shadows because that will help us constrain the thermal properties. So we're looking forward to doing that. And with that, I will leave this slide and I thank you.
Questions for Kerri? Go right ahead.
Hi, Kerri. I was just wondering, the landing plume is going to blow away some of that really loose superficial regolith. What is that going to do to some of the L-CIRiS's readings, if anything?
Well, it just means that we should be able to not only see areas that are closest to the lander that will be obviously scoured by the plume, and we're hoping that off towards the horizon, we will also be able to get some measurements of areas that are not disturbed Either way, we will be able to understand just basically how the thermal inertia, the thermal physical properties of that upper layer is changed from the plume interactions. And again, hopefully we will get some pixels that are not affected by the plume scouring, and that will allow us to give a comparison between the undisturbed regolith and the disturbed regolith. And so that should be a really important measurement that we can make.
I agree. Thank you. Very cool stuff.
Yeah, thank you.
And we can save any further questions for the question time because it's time to move on to our next talk. Thank you, Kerri.